Hello, in this video we look at change from baseline by baseline plots. And if you stay to the end, there's a very specific reason that I'm covering this topic. And in my opinion, it's kind of exciting to follow from an outsider's perspective. So let's let y equal the response variable and x be the baseline variable. And then we plot the change from baseline by baseline. And they're almost 100% always a downward trend. Actually, I've never seen one that's not a downward trend. And I've been doing this for a few decades. And I'll explain the math behind why there's always a downward trend. Now, if we look at this plot, we're really interested in, do the baseline measurements impact the response? And I think a lot of people create this plot to try to answer that question. And so, is there a correlation between X and Y by looking at this plot? And the answer is, we don't know. That we don't know just based on this change from baseline by baseline plot. Okay? And as mentioned, stay tuned to the end because I think it's a fun discussion that two people are having about this type of plot. So some of the math, and we're going to let X be distributed by some distribution at f of X and Y be distributed with some distribution G. Now they can be the same. So if you look at systolic blood pressure and then let Y be the 4-week systolic blood pressure after treatment, then you're interested in the response or the delta. But plotting it like this, I think is not the correct plot, and more on that later. So here we assume the variance of Y is sigma squared, and the variance of X is some constant times sigma squared. So if K is 1, they're equal. If K is greater than 1, the variance of X is larger. If K is less than 1, then the variance of X is smaller than Y. Now let's assume there's a correlation between X and Y. And ultimately, that's kind of what we're after anyway. So we're going to let it be rho, but the formula for correlation is covariance between those two variables divided by the square root of the product of the variances. And now, based upon the way we set this problem up, which I think is pretty darn reasonable and general, you get this. Now, if we want to focus on just the covariance of X and Y, we could multiply this over and we get this formula. And we're going to use that later. Now, stay with me here. The variance of X minus Y is the sum of the variances minus, and that's what the minus 2 times the covariance of X and Y. Well, variance of Y is sigma squared, K sigma squared, and the covariance of X and Y, so we plug it all in, and then we factor out a sigma squared, which is this. Okay, so that's the variance of Y and X. Now, let's look at the covariance of Y minus X and X, and the formula is this. You take the covariance of Y and X, which is this, and then it's the covariance of minus X and X, which is actually just minus the variance. And then we plug in the information, factor out a sigma squared, and we get this. Now, the correlation between Y minus X and X. So one reason we're looking at the correlation, because when we're in the univariate case and there's just an X and a Y, the correlation corresponds to slope. They're actually, it's a constant times the slope is the correlation, or vice versa. So they're proportional to. So if you have a significant negative correlation, you're going to have a significant negative slope, and vice versa. Okay, so the definition of correlation is the covariance divided by the product of the variances, and then we plug in what we determined, right? That's from this. That was the previous page. Variance of X is just K sigma squared. Now this sigma squared, the product can be brought out of the square root and cancel with this. And then it just leaves this. And now this is not a straightforward formula. But this is what exactly I want to unpack. And so there's 3 notes that if the variances are equal, and there's absolutely no correlation between x and y, so we plug those into this formula, we get -1 over the square root of 2, which is minus 0.7. So even if there's no correlation between x and y, we're going to get a significant downward trend based on this. And to me, that's kind of fascinating, but it makes sense, right? So if we're looking at the correlation of x and y minus x, well, we're sort of artificially putting a correlation on this, right? Because we're introducing that variable into this variable. So now the limit as k goes to infinity. And what that means is the variance of x is so large compared to the variance of y. Doing this subtraction, y plays no part in that variable. And so really it's just like having minus x. And so the correlation of minus x and x, well, that's -1. Okay, and I'm giving you sort of the 3 extremes, and we'll discuss more in just a second. And so the variance as k goes to 0, so that says the variance of y is so large compared to the variance of x, this subtraction makes no difference, and you might as well just have the y here. So the correlation of y and x, well, by definition, we call that rho. So here's a plot of what's going on. And so note number 1 is this line right here. It's the k equal 1 line. And so we plot this formula for all for all rho, k equal 1, equal variances. And actually this is a circle. You can't really tell, or I can't tell on my little screen that I'm looking through. There's a hole right there in this line. But it's always negative. It's 100% negative. Now, if we're very, very close to perfect correlation, we would expect it to be sort of balanced around 0, right? Because 0 correlation is 0 slope. But this line drops down so quickly that if there's 0.9 or 0.8, there's a significant negative correlation which creates a negative slope. So any realistic correlation between our 2 variables is going to create a significant downward trend. And now point number 1 is this line here. So if the variance of x dominates the variance of y, we just get a perfect correlation of -1 for all rho, and that's using this formula. And then this one is just the opposite. So if the variance of y dominates the variance of x, this is it. This is the rho line. So if rho is 0.5, the correlation's 0.5. If it's -0.5, the correlation is -0.5. And then everything in between. So if k is greater than 1, every line pretty much comes really, really close, and then just jumps up. And then a little bit bigger k, so k equal 2, twice the variance, is very, 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 very low, and then all of a sudden jumps up. So any reasonable correlation that we can expect, we're going to get a significant downward trend. Now, if the variance of x is so much larger than the variance of y, there are cases where we might expect a positive correlation, so actually the line to go up. But that's so rare. And if you're subtracting 2 variables where the variance of y is so much larger than the variance of x, it's kind of silly to do so statistically, as you're not really gaining much information. Now, the same is true when k is greater than 0, that all these stay really, really close to the k equal 1 line, and then go down. Really, 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 there's always a hump, boom. But, in the limit, it goes to -1. Okay, so now with that background, I want to introduce these 2 individuals. So Dr. Shiva, and that's his last name, which I'm not going to try to attempt, he created a plot that he thinks is very convincing that there's voter fraud in Michigan. And the plot is actually something like this. And so we'll look at that and analyze that, or give you my opinion. And then Matt Parker examines Dr. Shiva's plot and creates another plot and says, no, this plot 100% debunks Dr. Shiva's analysis. Well, in my opinion, if I'm understanding both of them correctly, I actually think they're both wrong. And here's why. So Dr. Shiva creates this plot, and what it deals with is people coming in to vote in Michigan can vote what's called party vote, is they say, I'm a Republican, I'm voting all Republican, and then they're done voting. And so the probability of coming in and Republican party vote is what we're going to call PR. And then, but you could also say, no, I'm going to direct vote, and that means they hand you the ballot and then you kind of pick and choose what you want. And so there's a probability of voting for Trump in direct vote. Now, Dr. Shiva says that these two probabilities should be very close. If you're a party vote Republican and a direct vote for Trump, they should be very close. And so what he does, he wants to plot it, and he thinks that they should hover around 0, right? For each precinct. So there's 252 precincts, and I'm going to supply links to both of these so you can watch them and make opinions for yourself. And he doesn't know how to plot them. So initially he's going to plot them by precinct, but that, he doesn't do that. What he does is he sorts them by the proportion of Republican party vote. And so, these, since it's negative, end up being, because this difference is negative. So these tend to be Biden precincts, and these tend to be Trump precincts. But he thinks that the machines in the larger precincts for Republican are switching votes because this should hover around 0. And now, based upon what we learned up here, that's not the case. Let's say the variances associated with these two proportions are the same. That's the K = 1. And the only way that we're going to hover around 0 is if we have perfect correlation. And there's not perfect correlation here. And so any reasonable correlation we assume, 0.9, 0.8, this line actually drops down, and we're going to get a significant negative correlation, which means a significant negative slope. Okay? So it's artificially creating that negative downward trend. Okay, so with that said, I don't know if there's voter fraud or not voter fraud. I haven't really studied it, but you cannot conclude it based upon this one plot, in my opinion. Now, Matt Parker looks at his analysis and he wonders, well, why did you only create the plot for Trump and Republicans? If you're going to analyze it fairly, you need to also create the same plot for Biden and Democrats. So this is the probability you vote Biden in the direct vote, minus the probability that you Democrat party vote by probability you Democrat party vote. And Matt Parker says, whoa, if the negative downward trend here is indicative of voter fraud for Trump, and you get the same negative downward trend for Biden, that means there's voter fraud for Biden. But you can't have it both ways, so therefore this one plot debunks Dr. Shiva's analysis. And my thoughts on that is that that's not the case, and here's why. Let's assume there's two candidates, just Trump and Biden, and these are proportions. So the proportion of Trump direct votes is 1 minus the proportion of Biden direct vote, and this is probability of Republican Party vote, which is 1 minus the probability of Democrat Party vote. And so if you were to plug in those equations, this graph is 100% mathematically identical to this, right? So if this one is evidence of voter fraud, then this one also has to be evidence of voter fraud because they're 100% mathematically identical. Now, in this case in Michigan, there's more than two candidates. So the probability of a Trump direct vote plus the probability of a Biden direct vote is like 98 or 99%. So these two plots are almost or approximately mathematically equivalent. So the fact that we have a negative downward trend is mathematically shown that this has to be the case. And so like this plot down here, this point, this precinct is that one. This one up here is this one. It's actually flipped and then reflected. They're 100% identical. So this plot in itself does not debunk Dr. Shiva's analysis. Okay, well, I've probably rambled on enough, and I'm going to put links to both of these, and I encourage you to watch them both. Now, Dr. Shiva's video is a little bit longer, and so I watched it in 2 times speed so I could push through it. Now, one thing about Matt Parker, I actually love his videos. I watch every one of them. He is so enthusiastic about math and having fun math, and I watch every video. And so this is not an attack against Dr. Shiva or Matt Parker. I actually don't know him, and I feel like I know Matt because I watch every video. But that's just my thoughts on these 2 plots. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.